Hi everybody. We are going to be talking about the different types of analytical engines you can use to analyze network telemetry data. Now I'm going to be talking about the technologies. I'm not going to be talking about the vendors or the particular products you can buy, but I'll be talking about the sort of techniques they use and the implications those techniques have in terms of what you can and can't do with your data. You don't need to know any of this stuff, but simply to know that I actually come from a background of databases and big data. And when it comes to network telemetry, you are talking about big data. You're drinking from the hose pipe. So for example, with a small to medium network, it's quite normal to be processing about 1 million flow exports per second and probably about 1 million DNS lookups per second as well. And you've got to analyze those, process those, and come up with some answers. So we're going to be talking about the technologies. We're going to understand what they can and can't do. And the important thing to understand is that certain database engines or analytical engines can do certain things well. And the implication is that the other things they can't do as well at all. And maybe they, in a lot of cases, do them quite badly. So this limits what use case types each storage engine or analytical engine can deal with. And whether you're talking about peering analysis or DDoS detection, subscriber analytics or routing analytics, whatever engine you're using underneath is going to limit the use cases that you can look at. Just to get some definitions out of the way. So when we're talking about acquisition, we're talking about acquiring data into our analytical engine. Performance, we're talking about the rate at which we can acquire data, and we're talking about the rapidity with which we can return results from queries when we want to find data or analytical results. And a query is simply returning a result set from our data. An index is a data structure which you build on top to make your queries faster. Partitioning is about a way of dividing up your data to effectively scale out performance. And drilling down is simply to look at some of the data that sits behind an analytical result. So the 4 technologies we're going to be looking at are streaming analytics, row stores, column stores, and Hadoop. I've shown some examples on the right-hand side. These are by no means exhaustive. They simply indicate the sort of technologies that are used in those particular products. And in particular, Apache Storm, for example, is for streaming, but also Apache Kafka, which has some added bits to it, which I'll talk about in a minute. But the important thing is, if, for example, we're talking about a row store, which we're talking about Postgres, or we could be talking about Oracle, they're fundamentally using the same technologies underneath. There might be some small percentage points in terms of performance you can get from one or another, but they're all pretty much using the same technology. So let's start looking at streaming. So this is really where I'm not necessarily storing the data. I'm just really have a bunch of queries sitting there, processing data as it arrives in real time. Generally, a streaming engine doesn't need to retain any of this historic data, although Apache Kafka is a variation to that. It does actually keep a log of all the events, which can be reprocessed if necessary. But I'll come on to why that may not be particularly useful in a minute. The implication of the streaming engine is that actually you can use it for real-time analysis, and it avoids any performance limitations of storage. If I have some sort of analytical engine which has to store all the data and reprocess it later on, then it's got to do things like IOs to get access to that data, and the performance of that is going to be limited by the storage performance underneath. With streaming, that doesn't really occur. I just have some stuff sitting in memory, I have data arriving, I'm processing it in real time, and I'm spitting out the results. So clearly you're getting data in real time immediately as new data arrives. The downside being that you have to know in advance what your queries are going to be, what your use cases are going to be as well, in order to get the results out. Also, because of the way queries are evaluated with incremental addition of data each time, that limits the sort of query constructs you can support. You can't do every type of query because there may be limits on the context space you can have available to you at any particular point. So you need this prior knowledge of your queries. If you make changes to your queries, then you're very limited in what you can do. With Apache Kafka, you can actually rerun your queries against the event store. But as I mentioned earlier, if you're talking about 1 million events arriving per second, with a day you're talking about 100 billion events, and after a month you've got about several trillion. And it takes a long time to reprocess all that data. So just keeping an event store, changing your queries and rerunning through the events doesn't necessarily give you a practical solution. And ultimately, you can have the streaming going on. It can give you spit out results which give you up-to-the-minute information about what's going on. But if you want to drill into the detail behind those results, then that's not really possible. Next, we come on to the row store. And this is, for example, like Postgres or the likes of Oracle, for example. And these are kind of relational concepts. So on the top right there, you've got an example of a table which is split into columns and rows, a bit like an Excel spreadsheet. And the row store will store data in the most obvious way possible, simply row by row. As a new row arrives, it just appends it to the storage. If you want to find a row, you generally build indexes on top of this, and you can find them pretty quickly by navigating those indexes. So it's actually good for fetching detailed data when you know what you're looking for. It does rely on the partitioning and potentially index design to deliver that performance. If you have no indexes and you have a table which has got billions or trillions of rows in it, it's going to take a long time to scan that to find the results you want. And because of the indexing, which I'll get into a bit more detail in a minute, it actually limits the rate at which you can acquire data. Ultimately, again, you're storing this data as it arrives, and then after the fact, you're performing queries against that data, which means that your limit or performance is determined by the storage performance characteristics. Clearly, if we're storing data by rows, it's not particularly efficient for scanning just columns, because we've got to scan all the data in every row to find out what's in its column. And indexes, we'll find in a minute, actually create a significant storage overhead. So if you have a very highly indexed row store, it's typical for it to expand the storage footprint by 2-fold or more. Oh, one thing I should point out. So if you think about the row store and the bottom half of the diagram there, I can simply append rows to my store as new rows arrive, which means that I can collect all the rows together and append them in a single I/O. So, for example, with one I/O, I can maybe append something like 1,000 rows in that one I/O. When I start adding indexes, things become a bit more complicated. This is an example of a B tree, which is very common. It's the default index you get in most databases. There are different index types, and I'm just showing you an example of a B tree as an example of one type. But they all suffer their similar sorts of problems. So a B tree is really just a hierarchy of blocks. We have a root block at the top, and we have leaf blocks at the bottom. When I want to find, and each block contains a series of keys in it. When I want to find a key and a row that corresponds to that key, I start at the root block, I look for the next largest key, navigate down to the next block, do the same thing again until I get to the leaf blocks at the bottom. Then they finally have pointers to where my data sits, which is all great for queries. When it comes to maintaining this structure, as I add new rows and new keys, then I've got to add keys into specific blocks in this structure, which means I've got to navigate my way down from the root block to the leaf block, insert my key in that leaf block. So instead of doing 1,000 rows in a single I/O, I'm now potentially doing about 2 I/Os for each key that I need to insert. I've slowed down my insert performance by a factor of about 1,000, just with one index. As I add more and more indexes, it gets worse. So this is why indexes such as B trees really impact your insert and update performance in a storage engine. Okay, Columnstore. This is, rather than storing data by row, we store it by column. And actually this permits us to do very fast aggregation of individual columns. We don't have to scan the rows in order to find the data, we just scan each particular column. Which means that actually it's very good for doing aggregate or producing aggregate result sets. It actually has good data acquisition speed as well because it's a very simple structure to maintain. I'm not creating indexes here, all I'm doing is I'm splitting each row into the various columns and then writing those out. And I can collect together lots of column pieces before I write them out to storage. So very good acquisition rates. It's also good for compression as well because each column contains values which are all of similar data type, maybe a small subset of values, which compresses down well. So good for I/O. But of course, it is reading from storage, so it's going to be dependent on the performance of storage, a little bit like row store. Ultimately, though, it's great for aggregation, but it's poor for drilling down into the detail behind the analytical result. For example, if I want to look at particular groups or cohorts of results, and I want to see which subscribers or entities sit within that group, and I need to drill down, then the Columnstore isn't good for that. It's basically got to find those rows and it's got to recreate them from the column pieces. Then we come on to Hadoop, which essentially is an architecture whereby I spread all my data into a file system where the data is divided around a large number of files in a distributed file system. And I have lots of hardware clusters. When I want to find something, I pretty much scan those files in parallel. There is some partitioning you can add to it to make it faster for particular use cases. But ultimately, Hadoop relies on using large amounts of hardware to scan lots of data in parallel to find the results I need. It does give you good acquisition speed because there's not much of a structure to maintain per se. We're just appending to files. But performance does depend on the hardware resources available, i.e. the number of hardware servers. And it also depends on the workloads that are going on concurrently, because essentially Hadoop is doing a lot of scanning when I'm doing a query. It's saturating I/O resources, also saturating network resources potentially. And if someone else wants to do a query at the same time, then we're going to compete. And performance is going to be affected by the fact that we've got concurrent workloads. There's some design required in order to get performance, such as partitioning, and that will obviously favour certain use cases over others. So again, I've made decisions, and that's limited the use cases that I can manage with Hadoop. So these graphs show you some comparisons of row store, column store, and Hadoop. What's important to notice is that actually these are showing the time it takes to do different query types shown along the bottom, whether I'm doing a forensic drill down, finding particular records or rows for a small use case, a small subset of data, or whether I'm going all the way to analytical, broad analytical queries across my entire data set. And also on the right-hand side, we're looking at the time it takes to acquire data. It's important to note that these scales are actually logarithmic. And you'll notice a row store, for example, great for forensic stuff, assuming I've got the indexes in place, great for interactive and that sort of thing, but slow when it comes to analytical and acquisition rates. And slower to the fact that it's 10 to 100 to 1,000 times slower than some of the other queries. Then the column store is the other way around. Great for broad analytics, great for acquisition, but poor at forensic drill down. Again, 10, 100, 1,000 times slower. Hadoop, more of a mixed picture. Generally doesn't do very well with joins though. Joins often fail because it doesn't have the right enough memory or the right structures in place in order to form a join. A join is where you take one table with another table, join them together based on common column values. And Hadoop will require something like 10 times the amount of hardware to give you equivalent performance compared to the best performance you might get out of row store or column store. So Hadoop is really all about the hardware investment. So what do these different engines mean for the sorts of things you can do? So a streaming engine is all about real time. It's about collecting data as it arrives and giving those results as it arrives. So it's great for DDoS detection and bad actor detection and real-time dashboards. So anything where you need to know what's happening right now, maybe something where you need to act in reaction right now, streaming is good for that. But again, you've got to know what you're looking for before the data arrives. What it's bad for in that respect then is if you have some ad hoc query or some ad hoc use cases you hadn't thought of before, then you can't go back and look at all your old data and say what happened. So for things like unanticipated use cases or changing use cases or evolving requirements, it's not necessarily great for that because you can't retrospectively apply the queries. And if you do have an interesting result coming back, such as an indication of maybe some sort of attack, then you can't really drill into the detail behind that very easily to find out what were the elements of that attack. The row store is great for very narrow analysis. So if you're looking for information relating to a particular subscriber, or you're looking for information about something that happened in a very narrow time window, it's good because you can have the indexes in place to find that data and bring it back. It's slow for things like aggregation. So if I want to aggregate all the values in a particular, say for example, all the bytes sent or consumed over my network, it can be very slow because I might have to scan all my rows to get that information. Indexes can actually speed this up. So for example, I can create an index on one or more columns, and when it comes to doing the aggregation, I can use that index as opposed to going back to the underlying row store. But again, whether that works or not depends on whether I've designed the indexes ahead of time to support that particular use case. And because of those indexes, you'll generally have slow acquisition rates. And these indexes require a lot more storage. And also the performance is going to depend very much on the design of those indexes and any partitioning you need to put in. Column stores. So they're great for aggregation, such as peering analysis, looking at traffic by peers, for example, looking at network load across my network by device, nodes, etc., and also time-based volume analysis and trending. Again, good for acquisition and compression. I can acquire a lot of data and I can compress it down and store it for a long time. But if I want to drill down into the information that's sitting behind those results, not very good at all. Because of row reconstruction required and also the need to find those rows. And performance will depend very much on storage characteristics. So whether it's NAS, SAN, SSD, hard disk, will hugely impact it. Hadoop, good for data acquisition, but the performance really depends on how much hardware you're prepared to throw at it. So it can be a very expensive solution. Can require a lot of hardware to do even the simplest of things. When you're talking about hundreds of billions or trillions of rows of information. It will favour certain use cases over other because you have to make certain design decisions ahead of time. So how am I going to partition my data means that certain queries will work well and other queries which don't need that partitioning or cannot exploit that partitioning will perform slowly. It's not great for real-time use cases either. So if you need information right now, up to the minute, it's not really there. And it's heavily impacted by the workloads that are currently running on a Hadoop cluster at any one time. So these analytical engines, they can take on board all this network telemetry, NetFlow, IPFix, IP lease information, DNS responses, etc., all the rest of it. The volume of that, though, will affect performance, particularly for Hadoop and the column stores. So both Hadoop and column stores require or rely on scanning either files, documents, or columns. And as you increase the volume of data, it takes longer to scan them. And essentially, all of these engines become point solutions in one way or another because streaming engines require prior knowledge of the queries. You have to know what you're going to be looking for. Row and column stores are very asymmetrical in their performance. You know, they're either good at forensic or they're good at aggregation. They're not good at both. And Hadoop requires a good hardware investment to deliver even reasonable performance. So they're not none of these are a panacea for all use cases. And so you really need to understand what they're good at and what they're bad at to determine what you need for the sort of use cases you're going to support. Thank you. And any questions? Yes?
What type of backend do you use in your product?
Our own. It's not a row store, it's not a column store, it's not Hadoop, and it's not streaming. Happy to talk to you about it later on. And by the way, if you have questions after this, then we also have t-shirts to give away. Now there's a bribe for you. Okay, I've obviously underwhelmed you all, so I'll depart. Okay, thanks very much.